Hopefully everyone can hear me. I'm Kyle Temkin. This is Chris Patterson. We're both from Assured Information Security. We're here to talk about some of our work bringing Xen and testing out Xen on phones and tablets. Our emphasis right now is mostly on tablets. They're basically phones without cellular. We haven't brought cellular support to these devices yet. That's a much more complex issue, especially with things like 911 requirements. So we're really looking at the class of devices that includes phones, but mostly our emphasis is on tablets right now. So I'm not going to go too much into detail about who we are. I care much more, and I think you guys care more about what we're doing and what we are going to show you today. So first off, why would you want to run Xen on a phone or tablet? For me, the first and foremost goal is that it's really cool, right? So I love playing with things. This is a really neat opportunity to take Xen and try it on an environment that really hasn't gotten a lot of use, right? Xen on ARM is kind of the frontier of Xen, and ARM in general is the frontier of virtualization. So we have a lot of opportunity to make contributions, a lot of opportunities to run into those fun bugs that you get when you first try to bring up a system. So this is really a neat playground to play in. But since I don't get paid just to do things that are cool, there also are pragmatic benefits to using Xen on these kind of devices. Probably the biggest one right now is separation of critical and non-critical tasks. So if anyone have heard the pitch for OpenXT this morning or for Cubes, which are both environments to help you separate things at various levels of criticality. This is the kind of application that would be perfect for a tablet. Imagine you have your financial information, or you need to be able to remote into your work and access financial information, but you also want to be able to use Facebook and Angry Birds, right? Hopefully those two things are not meshed together. Hopefully those two things are not leading into one another. And being able to kind of have a rigid isolation at the virtualization level where you're isolating a whole machine is particularly valuable. And there are applications like bring your own device where if we really were to integrate well with the vendors, we could potentially start solving some of these problems and start separating people's work tasks from their home tasks, other things that people have focused on a lot recently. But there's also potential to extend the benefits beyond phones and tablets themselves. We already heard about an automotive display project, what was being driven by an experimental Xen. There's a potential here to take what we're doing on phones and tablets and extend it really to anything that has a touch interface. Right? So if you're running the integrated touchscreen on your car on a controller and you're trying to use that controller for any other processing task, it might be nice to have that rigid isolation so you don't wind up with the kind of bugs that we had a few years ago where people were plugging in special MP3s and taking over car entertainment centers. So being able to have a more rigid isolation there also has significant benefits. So when we were originally thinking about this presentation, the thought was that we'd show you guys a lot of the cool stuff that we did on tablets and be able to show you some of the neat stuff that you'll be able to do. But as we thought about this, the presentation kind of evolved to not just do we tell you about what we've done, but kind of show you what you would need to be able to do to get Xen running on your own phone or tablet, assuming that it's the kind of phone or tablet that supports this kind of application. So we're going to spend the next few slides first going through what you would need to get Xen on your own phone, your own tablet, and then we'll go into some of the stuff that we've done to make it possible to use that phone or tablet for some client virtualization applications. So question here is, Xen already supports ARM. You can run it on dozens of eval boards already. We support lots of processor families. The dozens of eval boards that we've tried it on are a huge, they're really a subset of the many development boards that could run Xen. So there's already a lot of support for ARM. Shouldn't we then be able to run Xen on most phones and tablets? And the answer is kind of a tantalizing almost, right? There's still a few things we need. So even if you have a phone or tablet that runs ARM, and we support ARM, you obviously still need the virtualization extensions. And then beyond that, the main problem we've seen with compatibility on most of these is the permission to run things in hypervisor mode. So when your system starts up, it runs a first stage bootloader. Often that first stage bootloader will either come with the system on the chip, right, or be signed by the system on a chip manufacturer. So this is something that's not typically mutable, especially if you're working with a consumer device. It's the kind of thing that tends to be easily messed with if you have something that's designed for evaluation, where you have a good relationship with the vendor. But if you're buying a commercial device, like a cell phone, those off-the-shelf devices tend to have that immutable first-stage bootloader. And so if that first-stage bootloader drops you down to supervisor mode, right, if it drops you down to the privilege level where you can't access hypervisor extensions, it's very difficult to get back up. We've gotten back up in a couple of cases by exploiting things like TrustZone bugs. But on a generic case, they're not guaranteed to be able to get back up, and it's going to be a lot of work. So what you really want is a system that is taking those hypervisor mode privileges and extending them all the way to the point where Xen launches. Right, the key there is that when you're in hypervisor mode, that is pretty much the only time that you can effectively install the hypervisor vector table, which gives you the ability to get back into hypervisor mode with the HVC instruction. So if you can't tell Xen, you can't tell a system how to get back to the hypervisor before you leave hypervisor, you're never getting back in there. So this is one of the main things that prohibits you from running Xen on a phone or tablet. So you're going to need to find the right device. And that means you need a device that has both the ARM virtualization extensions and right now a full-featured GIC. Right? That's the ARM generic interrupt controller that provides the virtualization capabilities for interrupt routing. Without that full-featured GIC, you'll still sometimes see devices that say they have the ARM virtualization extensions. The Raspberry Pi 2 and 3 are great examples of this. But Xen currently doesn't support this because we don't provide an interrupt path beyond the hardware-enabled one. Right? You also need an unlockable bootloader. That's a bootloader that lets you run whatever kernel you want, that will chain load into whatever you want to, if you want to say it that way. And we need to be still up in non-secure hypervisor or EL2. So we need to be able to install those vectors in order to return to Xen, right? This way Xen can actually set itself up and then switch to your DOM0. So those are your needs. If you can, you want a device that is supported by an open source Linux variant. So it is way easier to use a device if you can set the thing up and not have to worry about getting all the drivers working in an environment, not have to worry about coming up with a custom DOM0. Right, so an open source Linux variant is the key. There's lots of commercial and derivative Linux variants that have large blob drivers, things that make it really difficult to work with when you're trying to get this device up and running. A benefit is to have a device that's closely approximated by evaluation board of some kind. It's much easier to work with an evaluation board, and we'll go into this. And having an accessible UART, so being able to get to the UART of your phone or tablet makes debugging 1,000 times easier. So JTAG's nice too, but if you have to pick any one debug element here, having the UART is probably your out-of-the-box key. That's what you're most likely to get access to on a phone or tablet, and that's going to give you the ability to see your system booting up and to not be coding blind. So if you want to figure out whether a device runs with, boots into its final payload with hypervisor or EL2 privileges, it's actually fairly easy on modern versions of Linux because as Linux is starting up or Android Linux kernel is starting up, it actually prints out where you've started. So if you're on ARM32, you'll see that it started in hypervisor mode. If you're on ARM64, you'll see that everything is started at EL2, which is that hypervisor execution level. And again, note these only work bare metal. So if you're trying this on Xen already, you know it works. You don't need to see these messages. So don't be surprised if you are running an example Xen distribution, you go and look for these messages and think that I'm lying to you. It will tell you it's EL1 because Xen has already claimed the hypervisor ring by the time you get to DOM0. Right? Otherwise, you can add some code to your kernel to check, basically doing the same thing on older versions of the kernel. You probably do want to upgrade if you can, but if you have a device that out of the box is running Linux 3.1, for example, you can still build in some code to check before you have to go and move to a newer version of Linux to get DOM0 support. Right. Now, I say that you really want a nice open source Linux DOM0 distribution. I say that at least partially because it seems these days in the embedded space, everyone has decided to create their own. So we have been using the Pixel C, it's a Google tablet, as our main development and test board. One of the challenges has been that there actually is a separate variant of Linux called Linux for Tegra that has most of the Tegra hardware support. It's very different from mainline Linux. So even getting Xen to run on there is a challenge. Fortunately, the Android team and Chrome teams actually have their own forks of the Linux mainline kernel that have a little bit better Tegra support. So what we're running on is actually kind of a compilation of all the best of all of those onto the mainline kernel. If you can avoid that situation where you have to deal with Linux forks that are heavily divergent from mainline, by all means do so. A good way to figure out whether your device has good mainline support is just to look at the device tree in mainline. There are lots of devices that have a device tree in mainline, and there's basically nothing in that device tree, right? So the device tree is going to describe all the hardware ideally for your device, all the hardware that you want to be able to use. If lots of things are missing or lots of things are different from the devices that are typically supported in mainline, you're probably not going to have a good time. Right, so you're going to need to do a lot more work to get this up and running. Then if you can approximate your tablet with a development board, that is definitely a blessing. Usually they bring out things like JTAGs, stuff that make it a lot easier to work with, and you don't have to worry about the environmental differences between your tablet and an environment that's friendly to Xen. Right, a lot of these tablets have custom bootloaders that are not present on the evaluation versions. So if you can test on the evaluation board, that's going to give you a nice clean environment where the bootloader is more likely to be transparent to you and more likely to be friendly, where you can test your initial experimentation. Right? And again, JTAG is just such a wonderful thing if you can get it. Some boards it's disabled out of the box, especially on Samsung evaluation boards. But if you can get one, it makes a lot of difference, especially in doing the initial boot startup before everything's relocated. Most tablets, you'd be surprised, actually do have UARTs somewhere accessible on the tablet. Sometimes you have to open them up to find that UART. Sometimes you don't. If you look around and search online, you'll actually find that we've, as a community, have documented a surprising amount of these outside the Xen community in the embedded Linux space. So you'd be surprised how often you can find details as to where a UART is. In a lot of cases where you can't, if you're capable of opening the device, it's actually pretty easy to find it with an oscilloscope. So, and I say it sounds pretty easy. I know some people are going, I have to use a scope, but it actually is a lot easier than it sounds. You take that scope and you point it around until you see a waveform that looks like UART. So, is wiggling at the right frequency. And you can almost definitely find this on a lot of especially cheaper tablets. So this is the Primo 73, which we've run Xen on. It has both an internal UART, or if you want to, you can program its bootloader to switch that UART out over the SD card slot. So you sacrifice the SD card, but gain UART access. A more complex UART is on the Pixel C that we worked with. We actually had to do a little bit of, I'll almost call it reverse engineering, except that all of their bootloader and all their startup code is open source. So we reverse engineered the hardware based on a lot of the software that was poking with the hardware. We were able to find that it does actually have a serial port that's exposed on 2 of the normally unused USB-C pins if you put 2 of the right value resistors on 2 of the configuration pins for USB-C. And so we did the work. You don't have to. You can actually follow either this schematic or on our GitHub, we have a full PCB design for a debug adapter for the Pixel C. So you can plug that in and be executing serial. Of course, after I designed the initial one, our intern had to go one-up me. So he has an even better design. The link is here. The slides are on sketch.io. So you can actually go click that link and see the hardware. You could build one yourself if you're willing to do a little soldering. Right, and that will get you UART access, even on a tablet that you can open. All right. Once you've selected a device and you have a pretty good shot at getting Xen to run, the trick is just to get the Xen kernel to start at all. Not necessarily run, not necessarily thrive, but get into Xen and get it booted, right, or get it to crash. Start off with a simple custom Hello World kernel. That's my recommendation. You don't want to be messing with image formats when the time comes to load Xen. There's a lot of things that can go wrong as you're starting things up. You really want to have the absolute minimum surface area so that you know that you're interpreting whatever your tablet's image format is correctly, and we'll go into that. The next step is to boot the Xen kernel alone. Probably the happiest day on this project was when I was finally able to see Xen Crash. So I went and looked at this, wrote my own custom bootloader for this that I'll go into, and then at that point, I was able to see Xen say, hey, what the hell, you haven't given me a device tree. And that was probably one of the hands up, most happy I've been to see Xen Crash ever. Right. After that, you're going to need to somehow get the required images to Xen. That's your DOM0 image, your device tree, things like that, and you can start to see how things behave. So the Hello World kernel is usually going to be a kernel that loads, prints something out on the serial, and then just sits there forever. Right? The goal here is to recognize that you're capable of transferring control to a custom kernel, and that you understand the image format that your tablet expects. So one of the unfortunate things about commercial devices is that nobody likes to agree on a standard. Even when they do, someone comes up with a standard and they usually will come up with a new one. So like Chromebooks have their own standard for the way images should be loaded. So they're actually fit images that are signed with a very particular header. Now, fit image sounds great, because those of you who run Xen on ARM know that usually most fit implementations will let you get all the images you want into the device. The Chromium OS fit image, of course, does not. We'll get into that. Many Android devices have their own special boot.image format, which isn't that complex, but there actually still is a special format that you have to put your kernel into, and that restricts what you can do with the kernel you start off with. And I've seen lots of variants in this format, including crazy signature schemes, lots of things that make it so that you have to do just a little bit more work to get your image loaded. Right? And most of these are documented either in the open source Chrome or Android repositories, the vendors' open source repositories they put out there to be GPL compliant, or by people who reverse engineered a lot of this stuff on the internet. I have yet to find a tablet that was completely wacky, that both had the capability to be unlocked and which didn't have a documented image format. All right. Once you compose your Hello World image, you can boot it and verify that you actually are loading the correct type of image. Right? It's also a great time to check for hypervisor or EL2 mode. That's as simple as checking the right bits on 32 in the current program status register on the equivalent for ARM64. There's actually a good starter example that someone wrote of just a Hello World kernel for the Nexus 9 that prints out basically Hello World and what the execution level is right on the serial port, which is accessible via the headphone jack. So really, a lot of this is just assembly that creates the correct image format, and then your little bit that prints your serial. Okay, so in this case, it prints the string hello, and then prints what the current execution level is. All right, so once you have knowledge of the image format enough to get a kernel booting, good next step is just to start Xen, built with early print case support, especially now as you understand how your UART works. Right, you can usually get early print case set up and just watch it crash. If you're here, you are over the biggest hurdle in setting your device up, because you know you can get into Xen and that Xen works in hypervisor mode. You can get in either EL2, this is not a Pixel C, or in non-secure hypervisor on ARM32. I had some interesting challenges trying to get our Pixel C up and running on, even just to get Xen to boot, because one of the things the Pixel C bootloader did not like doing was telling me where it put the TrustZone secure world. So there's a whole region of memory that it was not telling me about, where if I wrote the accesses were just denied, right, silently, and I wound up with writing basically zeros into these registers with no other visual outward appearance of anything but success. So that's interesting. Once you do that, and you're capable of getting Xen to crash, you're almost all the way there. The one thing that can still trip you up besides support for your system on a chip is the bootloader's image format. A lot of these image formats expect a Linux kernel in the appropriate format for the device. They expect it to be accompanied by a device tree, maybe an initial RAM file system. But all too often, they will not let you put anything else in there. So if you're trying to boot Xen, you want to be able to nicely get then the DOM0 file system, an initial RAM file system potentially, the device tree, and the Xen kernel. That's more images than just an Android image will allow. And since it checks the validity of all these, you can't go and do crazy things like on the Pixel C, you couldn't take the init RAM disk, which was expected to be in a particular format, and just shove Xen in there and say, hey, or shove the DOM0 kernel and then patch Xen to load it from that slot. Right? So most image formats on these devices will not load all of the images that you need. Now, you have an opportunity at this point to go and do the same thing you do on x86, right, where you read a boot sector and then start executing from there. You could put a single image in there and then load a second stage bootloader. And if you can, a good idea at that point, if you have the knowledge, is to take U-boot and shove it in there. So if you can take U-boot, wrap it up in your kernel's image format, that'll give you an opportunity to load those images into memory from anywhere you want, from an SD card or from one of the eMMCs on the tablet. We actually wrote a small toolkit that's a little bit faster and smaller than U-boot for our purpose. It's called Discharge. It's originally an adapter from the Google bootloader. Its payload is called DepthCharge. Discharge converts from DepthCharge to Xen. And all of this is a simple toolkit that takes whatever images you want and squishes them into a single image that appears to be a Linux kernel. Right? So just like the Linux kernel has its boot code on x86, which will decompress and load all the rest of the things you need, this has essentially an archive loaded into a Z image or a U image that loads the rest of Xen. That's also an option. If you have the capability to use U-boot, you have the space, you have the capability to just put arbitrary things and arbitrary spots on your eMMC, then by all means do so because U-boot is a lot more powerful than our little toolkit. But this is there for the rest of the time. And source code's all MIT licensed, you can do whatever you want with it, and it's all online. So once you do have Xen booting, the next step is to get Xen running on your system on a chip. Now, that sometimes is easy. There are lots of devices for which it works. We were targeting the Google Pixel C. It's a nice looking tablet. In that case, it was not so easy, partially because we're working with a new device family, the Tegra, and partially because there were lots of vendor surprises in there. One of the things that tripped us up immediately, when you started Xen, you'd see that there was basically no IRQ controller recognized. Turns out that was a change that needed to be made to Xen. The IRQ structure on the Tegra is very similar to the normal GIC structure, but it has some additional elements we have to handle, and I'll cover those, I think, on the next slide. Right. So you may have to deal with quirks for your particular system on a chip, or with Xen behaviors and bugs that are unmasked by your new kernel. Right, so working with your new system on a chip, there are lots of things that are set up by the bootloader that may not be in the configurations that Xen expects. You're going to run into some bumps. I submitted a patch based on the odd bootloader to ship with the Jetson TX1, which actually was selecting that anytime an interrupt happened, it would use the EL1 stack instead of the EL2 stack. So if you bumped up to the hypervisor, it would continue trying to use whatever the stack was from supervisor mode, which causes problems, especially if supervisor mode hasn't been set up yet when you're first starting to boot Xen. Right, so there's no stack. And that just manifests as the whole system just going dark. A lot of fun to debug. So that's been corrected and patched. You may find similar behaviors here when you go and run Xen the first time. I can't possibly help you debug every one of these on one slide, but if you do run into issues, the mailing list and the IRC channels are great resources. Right, so you may find bugs. This is kind of the frontier, especially on unusual devices, and you may have to deal with quirks for your particular system on a chip. So on the Tegra devices, normally you have what's called the GICS distributor. That's the generic interrupt controllers distributor, handling all of your IRQ distribution via these CPU interfaces to your normal CPUs. So normally an interrupt request is delivered to the GIC and populates its way over to the CPUs. If you set up the GIC correctly, you're capable of receiving those interrupts. On Tegra systems, there's actually a second legacy interrupt controller that also has the capability to mask IRQs. So it turns out that we had to write a Xen platform module to support the Tegra legacy interrupt controller. And to enable pass-through, we had to write some logic that enabled this legacy interrupt controller to be virtualized. So that is on our Tegra support tree. I'm waiting on one other patch to get in there that has to deal with an issue with Tegra serial. Once that is accepted into Xen, I will RFC all of this. This all should be mainlined. All right. So we're currently working on the whole process of getting that mainlined. I'm going to put out an initial RFC. We'll decide on what the right way is to do from there. But we do have everything working on with our solution. The question is really just whether we want to come up with a solution for the Tegra platform or whether there's maybe a more generic way to do this for lots of devices, which would be a better solution, and I prefer if we can. Once you have Xen starting, you run into the fact that you've basically created an evaluation board in a fancy tablet form factor. So all the additional devices that you have now have to be virtualized for a variety of your guest domains. So you're talking about displays that have to be virtualized, and you want, unlike like on a normal server workstation where you're only ever using the display for management, or on a desktop where you may be using something like XenGT to get your display by virtualizing the GPU. Really, on a tablet, you're trying to take whatever that display is and provide a native-like interface, right? The last thing you want is to have something like Android running in a tiny window on your tablet, right? You already don't have enough space on those screens. The variety of additional sensors you need to be able to use multi-touch, you need to be able to use things like light sensors, cameras, fingerprint sensors. In order to have the right experience, you really want to be able to virtualize as many of these as you can. And that's where we are right now. We've developed a lot of the platform, and we're working on the virtualization pieces in order from most critical to most kind of candy pieces, like your fancy flash LEDs, things like that. Every one of these needs 3 components to work. It needs to be supported by your DOM0 distribution. It needs a Xen backend and a Xen frontend. So to provide our guest with a high-performance display capability, we wrote a whole new display server for Xen that is designed for client virtualization use cases. So unlike Spice, QXL, VNC, this is designed to be the only interface you have to the device. It's not running in X. It sits atop the Linux DRM subsystem and provides you direct multiplexing of the full display. And that includes, actually in our display piece, kind of like how VNC includes mouse pointer for our virtualization. We provide full support for multi-touch input. So we actually have a multi-touch version of these Xen input drivers that we use to interact with these devices. And again, that's open source. I'm not going to go into a lot of detail about our display technology now. The next talk that's in this room after the break is actually a talk just on that technology, given by Brendan. So that will be in this room right after the break if you want to hear more. But it actually works pretty well, and I will give a demo after the talk to anyone who's interested. So a lot of the front-end and back-end drivers, the back-end is provided by that display server. The front-end are provided by extended versions of the Xen drivers. So we have an extended version of the Xen keyboard front that's shared with the OpenXT project. That's called OpenXT keyboard front. And that supports things like multi-touch. It's really just an extension on the existing Xen KBD driver. The only reason I haven't tried to push into mainline is there's no equivalent backend right now. So there's no support for that in VNC or Spice. If we work to get that, then absolutely would rather have this sitting in Xen KBD front of the Linux kernel than something that I have to maintain myself. So if we have the opportunity, definitely submit the patches. They're already backwards compatible with the Xen keyboard drivers. So adding that functionality doesn't take anything away. All right, and now I'm going to hand the one microphone over to Chris to give you a brief introduction to our Android efforts.
We're already past our. I'll be quick. So basically, we've done some prototyping with Android. There's a number of hurdles that kind of need to be overcome before we can really have a good user experience on an Android platform. And so the 3 that we'll talk about today a little bit, the first one, the big one, is actually the fact that Android requires hardware acceleration. And so if you're using a client virtualization solution, you need a way of being able to multiplex that host GPU to provide accelerated graphics for each of the client guests. Or you dedicated a GPU per guest that you have on your system. Another one is power. A lot of the mobile operating systems, they've done a lot of optimization to reduce power consumption on these devices. And so in a virtualized platform, you have to extend that to include the fact that you have multiple guests, your control domain, your hypervisor, so on and so forth. And so there definitely would probably be some work there. And then the third is TrustZone. So A lot of applications on Android require the use of trustlets, and being able to extend that to a virtualized environment has some challenges that we'll talk about. So accelerated graphics. So Android Surface Flinger, as well as various Android applications, kind of require OpenGL support. OpenGL ES 2.0, I think, is the minimum today. And so there's a number of options that you kind of have to be able to provide that. The first one is some sort of software rendering, if you don't care much about performance. Taking something like LLVM pipe, which works on Android x86 today, and being able to utilize that. Or some sort of virtualized GPU solution. If you're on an Intel platform, perhaps Xen GT is a good option for you. If your hardware supports it. Samsung did a demonstration a few years ago, I believe, at Xen Summit on one of their tablets. They had some sort of proprietary solution. And a promising option is VirtIO's Virtual Device. And so Rob Herring from Lenaro has actually done a lot of work on getting Android running inside of KVM, utilizing the graphics acceleration provided by the virtual device. And so being able to take that, well, we've done some prototyping of seeing Virtual running on Xen. In order to do it on Xen on ARM, you have to provide a PV transport for that VirtIO device. And so that would be a kind of a biggest hurdle to being able to utilize Virtual on ARM platforms as well to provide that graphics capability. There's other options such as what Android uses in their emulator, EmuGL, which provides their graphics support when using emulation. It's unclear exactly how performant that would be, particularly on a mobile device, but it's certainly another option that could be considered for integration. That relies on something that they have called the commute pipe that interact with the host. So there's certainly options. There's no option that strikes as being the best option for everything, but we're leaning towards kind of seeing what it'll take to basically take that Virtual and add the PV transport so it's capable of running on all platforms, ARM, Intel, and so on and so forth. TrustZone. So TrustZone architecture today basically provides some challenges on client virtualization solution, notably per guest services for TrustZone and enabling multiple guests to have access to the services that TrustZone provides. And being able to do it in a way that's both safe and secure. So, if you look at the Qualcomm bug that came out a while back, they had an issue where you can escalate privilege on the device by breaking into TrustZone. It's kind of a black box, and so enabling some sort of service like that, having your VMs, your guest access something like that provides additional attack surface for your virtualization solutions for the guest to be able to break out, not just out of the VM, but have pretty privileged access over the entire system. And so one of the questions is, how do we kind of take something like that? Can we multiplex it safely? Can we maybe move the trusted execution environment into its own service VM? Can we kind of provide it as, instead of being protected by a mode provided by the processor, maybe we can just encapsulate it within a virtual machine if your platform distribution relies on virtualization to begin with. And so there's certainly options there. A lot of research is required. If anybody has any ideas on how we can accomplish this, that would definitely be very interesting to talk about, and it's probably worthy of a more significant research effort in and of itself. So the last thing I want to talk about before we finish this is the Xenbedded distribution. So right now we're actually still kind of locked up in an approval process to get that open source. It should hopefully happen anytime soon now, but So, so basically, it's what we're using to kind of provide as a distribution layer for building images for the various machines that we're targeting. And so it's actually based on Open Embedded. I don't know how many of you are familiar with it, but It's a pretty powerful cross-compiled build system for building images, kernels, and so forth for your board support package, basically.